do it. Hello, hello. All right, folks, take your seats. We're about to get started. This is the CFRG. If you're here for another meeting, it's not in this room. Okay, we've got a pretty full agenda today, so we're going to kick it off with the chair slides. Lexi, take it away.
Hello. So yeah, I'm Alexei Melnikov and Nick Sullivan is sitting next to me. Stanislav did a lot of stuff in background, and I believe he's enjoying his holidays at the moment. So just quick update from chairs, the usual stuff. This session is being recorded. We have a minute taker. Thank you, Joe. Please don't forget to log in, whether using the full client or local only client. It helps keep track of who is in the meeting so we can have a proper room allocation. So the usual, I hope you've seen the note well. If you haven't, you have some documents to read up. So this is about intellectual property and participation. Okay, so as I already said, we have an audio and video recording. We have some presenters who will be remote, so please use the tool to get yourself into the queue. And please follow code of conduct. In particular, be professional and be nice to each other. We probably should have updated the slide on masks. I think that's probably mostly a non-issue now, but anyway. So as a reminder, this is IETF. The rules are a bit different from the rest of IETF. We do work on cryptographic primitives, but we do quite a lot of research and more experimental stuff here as well. So this is our agenda. We have a lot of quite short updates on various documents. We have a lot of document in flight at the moment, so which is, I think, is a good news. We wrapped up several, or they're close to being published, and a lot more will be following up. Any agenda bashing? If not, we're doing a usual couple of slides on status of various documents. I'm not going to read every document. So we have several finishing up, actually, being in Note 48 now. So just about to be published as RFCs, some are being edited by RFC editor, none currently in ISG review, but one in our RSG review. We're not waiting for our RTF chair to do anything, so it's all either in the research group or in post-processing. And as you can see, we have a lot of document in flight. Majority of them were updated recently, so this is all good to see, and we'll hear updates on many of them today. If you see anything on these slides which you think is not accurate, please let chairs know. Okay, and with this, let's go to the so and Nick is going to talk about the new document that got recently adopted is guidelines for writing cryptographic specifications.
Okay, this is going to be a pretty quick update to refresh people's memories. Last time presented an idea around having a document to help specification writers, specifically in the IRTF and CFRG, to help make it clear what the expectations of these documents are to help lead to higher quality written outputs from this group. Next slide, please. So there's a number of use cases for this, or a number of reasons that this is beneficial. I don't need to go into all the details here, but a draft was shared on the list, and it got a certain amount of positive feedback, mostly all positive feedback. So next slide, please. So I'm just going to review a couple of these pieces of feedback that are intended to be addressed as the document continues as a research group document. One that was brought up was references to previous RFCs. This was a little bit light and sort of not keeping in the IETF's tradition. So having more references to the deep knowledge that we've shared together at the IETF is going to be one piece of feedback that we addressed. The second is use of standard mathematical symbols. There was kind of a joke put in there to see if people would notice, and people did notice. So there's questions around the debate of group operations, whether they're multiplicative or additive, whether to use non-ASCII symbols and things like this. This will all be cleared up and discussed on the list. There's some questions about some terminology, like formality, like what does formality mean? There's always room for a more detailed glossary in a document like this, and that's something that will be addressed. The next point here is broad support and review commitments. So this was a part of the positive feedback. A lot of folks on the list said that they'd be willing to review and provide comments on this document, and we appreciate that. The last piece here is something that wasn't fully fleshed out in the document, but was recommended as something we should do, which is parameter choice. One of the biggest things that people debate and bike shed on over cryptographic standards. So having more detail about that is something along the line. And so that's about it. The document is adopted, and it's going to continue to be worked on from this point onward. So any questions? Anybody online? Nope. Is there anybody on the queue online?
Yes. Chris Patton, Cloudflare. I think this document's awesome. I think the most important, I was one of the people who complained about like the definition of formality and how it means different things in different communities. I think the most important thing we can do is make our documents self-consistent. So I think that if that's like the kind of the lowest common denominator, I think that's perfectly fine. So yeah.
One vote for consistency, which is also one of the sections in the document.
Jonathan in the chat said that using Unicode for double struct letters would be really useful, but not obvious it's allowed under RFC 7997 rules. I think it is actually. And the use of mathematical symbols in general is probably the better use case for using Unicode. So,
So someone mentioned this the other day, and I had a look, and I read RFC 7997. Sorry, Jonathan Hoyland Cloudflare.
Yeah.
And it says in the text version of the spec, like .txt version of the spec, you just have to write out the bytes, like as letters, and only in the PDF do you show what the letter is. And that would be really hard to read. Like it's, I'm not sure double struck N is, I could recognize the bytecode for that off the top of my head.
Right.
Maybe. I guess I could learn a new trick.
Colin Perkins, there is at least some discussion about relaxing that.
Well, I'm in favor. Where's that discussion happening?
The RSWG, the RFC series working group, which is meeting on Thursday. And just, I'm unfortunately the document author on the one that is discussing this. Don't take anything that you read set in stone.
Yeah, I was just going to say, I would really like to use Philhan Baker. I'd really like to use mathematical symbols. I've tried, and the current tooling doesn't support it. Well, they disappear and turn into blocks when I try and use them. So, you know, it'd be good if this group said that this is something we would like to do, and that's probably the way to have things happen.
Hi, Colin Perkins. So the RFC editor does support non-ASCII characters in RFCs. There are perhaps some rough edges around the tooling. There are some issues, some policy issues which need to be resolved. But we have had a number of RFCs that have non-ASCII characters in them. So if the group thinks it is a useful thing for clarity of the specifications, then we can work with the RFC editor and it will happen.
Okay, thank you.
thank you. All right. Thank you, Nick. Okay. Next is Tobias. I'm going to, all right. Do you want to try it? Do you want to share them? Or? No, that's just fine. Just saying slide. Oh, yeah.
All right. My name's Tobias, and I'm presenting on a current work item, the BBS signature scheme. Next slide, please. So just a bit of a recap on this scheme. There's three protocol participants, a signer, prover, and a verifier. The fundamental properties of the scheme is that it's multi-message in nature, in the sense the signer can sign multiple messages, and it supports selective disclosure from the prover's perspective. And these proofs are said to be zero knowledge proofs. Next. So as previously said, next. So the prover is basically in possession of a signature produced by a signer that protects a set of messages plus a header. The header is basically a payload section that must be revealed to all verifiers. And the multi-message payloads are the ones that the prover can select within in which to disclose. They generate a zero knowledge proof, which is basically a proof of knowledge of possession of a signature. Next slide. And the verifier can then basically prove integrity on those revealed messages and the revealed header, guarantee authenticity of them back to the original signer without knowing the exact signature that the prover was in possession of in order to generate that proof. Next slide. So just a few updates since last time. Today, it's obviously we've published draft 03 in preparation for this IETF117. The basis for most of these updates came through some new work from academia. There was a recent paper published in Eurocrypt that revisited BBS signatures in the construction documented in our draft. And they managed to find some additional efficiency improvements, as well as reproving formal security. And in that effort, the optimizations have ultimately led to a ability to remove one component of the signature and a few components of the proof in order to improve the compactness. Those numbers there, just for note, are based on the BLS 12381 curve. Obviously, signature size and proof sizes are somewhat dependent to the field size. So there is a link to the paper below for those that are interested. Next slide. Just a quick note on what we observed in our implementation and implementing these is the sign procedure, verify, proof gen, and proof verify all found notable improvements in performance. Next slide. Some other things that we've done in this draft and the latest is within the Cipher Suite definition, we have worked upon documenting in a Cipher Suite like extensible manner two kind of functions or procedures we call generator creation, which are fundamentally the public parameters that are involved in the scheme. So generators refer to basically the points that we commit messages to and how we manage those public parameters in a way that keeps implementations of the scheme simple. And then also the message to scalar mapping procedure, keeping in mind that we believe that additional Cipher Suites in future BBS may want to do different forms of scalar mapping, such as ranging integers for like predicate proofs or the likes, whereas the predominant mapping procedure we use today is basically hashing a message to scalar. So we've just really rejigged a bit of the document to provide that further extensibility in future for those that want to extend the scheme with new Cipher Suites. Next slide. This is a little bit more sort of details on that create generations procedure, how the current procedure actually works, which is basically a feedback encounter mode, and also how Cipher Suites, if they so wish, can extend it. We needed flexibility. I think it's important to sort of highlight here, different constructions of the scheme may want to use existing like public well-known points, like the base point in a field, so they can, one of the messages could be a ordinary sort of public key. So the generator kind of creation procedure needed to be parameterized at the Cipher Suite level to support that. Next slide. And again, next slide. And yeah, so again, with the map message to scalar, as I previously sort of said, the use cases here for flexibility are really around things like Calder binding and the predicate proof. So if you want to take scalars and make them messages and map them so that they can be used with range proofs, like extended sort of zero knowledge proofs, that makes this compatible. Next slide. And next slide. We also sort of adjusted the Cipher Suite ID for the different Cipher Suites to capture that these things are parameterized, so that we have good Cipher Suite separation in future extensions. Next slide. Some other more sort of editorial updates. We kept the test vectors in the core document for now, given the kind of feedback from the previous IETF session. Still considering moving them out later. In the meantime, we have added new test vectors. We had some feedback that we didn't have any using variable length messages, and we also added some tests in for no header or no presentation header, just so that interoperability can be facilitated for those cases. We updated the error handling to sort of talk about where we expect implementations to abort. And we also shifted the KDF to a hash scaler instead of HMAC. So that was really in a pursuit to sort of simplify the primitives we were using within the draft. Next slide. And that's it. Any questions?
Hey, Chris with Cloudflare. What's the status of the implementations of this? You mentioned that you have an implementation. Of course, I tried to check the GitHub and I couldn't find any. So I'm just curious if you know of more, and if you do know more, could you collate them into a single list so we could test stuff out?
Yeah, really good question. Ahead of this IETF meeting, I think I'm aware of 3 others other than ours that have updated to draft 3. But we will collect them into the repository so it's easier for people to find them, because I think all other than ours is to be open sourced. Everyone else is already open source, I believe.
Lovely, thank you.
Watson Lad, Akamai. I think I needed this draft earlier in Privacy Pass, and I'm glad I was aware of it now. I'm a little concerned that you might be expanding the number of use cases in a way that doesn't necessarily tell people who want to use it what it is they need to do. And also, when you have a Eurocrypt paper from a few months ago and you're putting it into a draft, that the amount of effort required to really review that and make sure it's right is still quite a bit compared to if it was just sticking with BBS from the original publication, because that's been looked at a lot more.
Yeah, so the reason those academic authors wanted to, I understand, like, the draft also points to the previous academic literature as well. But there were some changes in the setting that this Eurocrypt paper, so it's a revisiting paper. It's not a completely new scheme.
But would those changes impact the security analysis in a way that we might have to look at more carefully?
Well, my interpretation of it, and it'll probably be something for the academic authors to comment on, but they think that it is actually a contribution that further strengthens the security rather than kind of resetting, building upon previous work.
Armando Faz, Cloudflare. So you mentioned that you changed in your last slide about KDF. So my question is there any motivation to use extendable output functions rather than defining everything on SHA-like?
Yeah, so we originally had usage of extendable output functions, but we wanted to, in the draft at least, try and we originally had usage of XOVs in other places as well. However, we kind of reorganized some of the primitives from hash to curve, some of those to make use of them instead. And we kind of got to a point where the only place we would use an XOV would be in the key generation function, because this is a key generation step, right? So implementations are actually kind of free to generate keys however they want. It's more of a suggested way, a secure way to take an IKM and generate. Does that make sense, or?
Somewhat.
Okay. Vasilius, a co-author, might be able to speak to it.
Thank you.
A little bit more.
Yes, hello. Vasilius Kalos. I'm one of the authors of the draft. We do have support for extendable app functions. One of the assumptions is actually based on Scikit 256. So throughout the draft, we do use XOF functions, but through the primitives defined into hash curve. So you can use expand message XMD, which is just a plain hash function, or expand message XOF, and we define substitutes that use both. And whatever you use, that will be used to derive the keys, if that makes sense. Okay, thank you.
Thank you very much. Okay, so next is Frank. I don't. The presenter seems to be remote, and we might need to reshuffle this if he's not. Doesn't seem to be online at the moment, which is quite unfortunate. Okay, so let's Scott.
Okay, this is going to be a very quick note about, I've been asked to talk about the latest LMS parameter set draft. Next page. Very quick history. We created LMS, a RFC 8554 a while back, which is defines a stateful hash-based system based on SHA-256. We were asked to expand these choices. So Quinn and I created Graph-Fluor LMS more parm sets. This defines, includes a 192-bit SHA-based hash function, which about halves the size of the signature. And there's also a SHA-256-based version at 192 and 256 bits. The 192 function, of course, drops you from level 5 to level NIST level 5 to NIST level 3. But again, it has the size and still is quite conservative. Next page. IANA is actually assigned code points for these new parameter sets, and they're also standardized in this publication 800-208. The only thing that I've been told that is waiting on is a few more people reviewing it, and so would somebody please review it? Thank you. And also one other thing, I've also been asked whether or not we should standardize the format of a private key which is exported. I'm not. If we do that, I suspect this should not be in this draft. It should be in a separate draft. Okay. Any questions?
Bas Esteban, Cloudflare. I'm happy to review the draft.
Thank you.
Have you considered 128 bits truncated hashes parameters?
How big?
128 bits.
We did consider that. I had a conversation with NIST where we decided not to go that size because we're not quite comfortable. If you're going to do the stateful base hash function, level 1 sounds a little bit too close. But again, if somebody wants to add a new draft with it, wouldn't be opposed.
All right, thanks.
Yeah. Yeah.
Thank you. Probably should have asked him whether he wants. Andre, you're next.
Yeah, hi everyone. Well, today I'm going to give a talk on properties of AED algorithms draft once again. Well, next slide, please. Well, since last IETF meeting in actually March, nothing much was done with the text of the draft. We haven't published a new version. There were some minor changes in the text. This is due to the fact we are taking a short pause for research stage. We are looking for some, as outlined previously, we are looking for some functional applications which require unusual properties from AED algorithms. And the next version is scheduled, luckily, by the next IETF meeting. Next slide, please. And speaking about looking for part, if your application, if your protocol has some specific requirements for AED, please let me know. I would be really happy to hear from you. Next slide, please. In this talk, I also want to address a question which I receive quite often. It is about classification of how we classify properties in the draft. We divide them into 4 groups, like basic security, additional security, implementation properties, and additional functionality. And with 2 of these, everything is quite clear, but with security properties and additional functionality properties, the distinction between them is a little bit vague. Next slide, please. If we speak about security, about basic security, we usually consider some non-respecting adversary who wants to break usual confidentiality and integrity. Like it is the basic setting, it is the basic security for AED scheme. And if you want to achieve some additional security, next slide, please. We extend what an adversary can do or it wants to achieve when communicating with that scheme. Like it can we allow him to repeat nonsense in inquiries, or next slide, please, or allow him to we consider an adversary which wants to make many forgeries at once. But with next slide, please. Thanks. But with additional functionality, situation is a little bit different. Like when you have some product and you add some additional functionality to it, you usually change the interface of your product because it has to return new data or it has new inputs. And we follow that approach in the draft too. When speaking about additional functionality, we say that property is additional functionality property if it implies different a change or extended interface. With incremental AET, you have a new function, update function, and next slide, please. And when you consider when you change interface, you actually change, you define a new class of algorithms. It is in some sense a bigger class than usual AET, and for that class you have to redefine basic threats, redefine basic adversarial capabilities, and it is a new distinction between additional security properties and additional functionality properties. You can analyze every casual AED scheme for having additional security, but you cannot analyze it for in this new sense of new basic threats and new basic adversarial capabilities, because you even can't put it in security model due to different interfaces. So this is rather theoretical, and but I think that classifying and finding a way to classify properties is a good way to find a common language. And if you have some opinion on that, I would be happy to hear from you. Well, that's all. Next slide, with context.
Any questions?
Watson Ladd, Akamai Technologies. My question is sort of in this sort of breaking down of the properties. Let's say you look at something like a cipher that's one pass, and because it's one pass, it can't be fully robust to nonce resistance. Instead, you're leaking a certain amount of information, namely the length of a common prefix sort of thing. Does that fit into the overall splitting up of the security properties? Or I'm just worried that sort of some of the terminology you have these terms online, you have nonce resistance, you put them together, and you don't really have a language to talk about things that might not be as robust as other things.
Well, speaking about one pass, I guess it is more implementation property, but when we some implementation properties can influence like security properties and connection between them. There is some connection. You can't achieve some implementation properties without losing security properties. But these properties by itself, I think, then they can be divided like in some different groups.
I'm first of all, I think this is thank you for doing this work, because it's like there's such a nebulous big space, all these AEAD papers. I want to throw one more at you. I'm wondering if you saw that paper from I think Barbosa in 2018. He called it indifferentiable authenticated encryption.
Yes.
I just want to hear your take on that paper and how it might or might not fit into this draft.
I have it like I actually really love indifferentiability. It is like one of my new favorite things. Not only about AED but about hashes, and I like it. It is in a queue. I have to study it a little bit thoroughly because it is new. But I'm going to think about that and add it to somewhere. I think it is security property in some sense. Yes, thank you for the question.
I think it would be really cool to see security proofs for like normal, like, I don't know, probably you have to start with like a robust AE scheme, and you prove that it's indifferentiable when AES is a ideal cipher or whatever.
Yeah.
Yeah, I think that would, maybe be the tool to rule them all. Maybe, probably not.
It is very interesting, and like indistinguishability and indistinguishability are related, so it might be really cool. Thanks.
All right. Thank you very much.
Thank you.
Dan?
Yeah, thanks, Dan Harkins. So proposal to add some features to HPKE. So next slide. So some of the issues with HPKE is it has some bloat. When you use the NIST curves, the serialization of the public key is more than twice as big as it really needs to be, which can be an issue for constrained devices, and also for use cases where you can't amortize the overhead with a whole bunch of packets. Another issue with HPKE is that it assumes guaranteed in-order delivery of packets, and that's not really how the internet works. And this is bad because if packets were reordered or dropped, the HPKE context would become out of sync, and there's no way to even realize that happened or to resynchronize. Everything just goes south. So there's no way to debug it. It's just all of a sudden things stop working and you go, oh, well, that's not good. The other issue is key wrapping wasn't really a guiding point of doing HPKE, but I think it is a valid and obvious use case. It would be nice to have some key wrapping support. So next slide, please. So what the draft proposes is to add compact representation of public keys for the NIST curves. This is a la RFC 6090. This would defines new chems and new serialization and deserialization. It also proposes to add deterministic authenticated encryption from RFC 5297, which is the specification of the Rogoway-Shrimpton paper from Eurocrypt, which will address provable security treatment for key wrapping, and also address the lossy network use case for certain types of traffic. For certain types of traffic that can't use DAE, the draft proposes to add an RFC 2401 style anti-replay window to deal with lost or reordered packets in a certain window. So next slide, please. That's the draft. And there is source code. The source code is completely compliant with RFC 9180, and it also includes support for compact representation for the NIST curves as well as DAE ciphers. there's complete test vectors for both of these things. I stole some of the numbers reserved to IANA to generate the test vectors. So if I have to change them, it should be pretty easy to generate new test vectors. Next slide, please. So the draft's pretty stable. The code is very stable. The drafts are currently at 01, but it was based upon an 02. So technically, this is maybe the 5th version of the draft. There hasn't been a whole lot of discussion on the list, but there's already been some cases where I'd like to propose these features in different protocols. And it would be really nice if we had an RC to point to instead of this draft. So I'm hoping maybe we can get an RGLC call. And that's it.
Thank you, Watson.
Watson Lad, Akamai, in case people haven't heard it before. I think when I look at this draft, there's nothing that stands out as really wrong, but I guess if you are talking about communicating nodes over a lossy channel where you might have these retransmissions, why aren't you doing something interactive to set up a session transport key? Because it feels like maybe what you're doing here isn't quite right for the application. It's a very different context than where HPKE is really analyzed. And that I'm worried a little bit on security implications there.
I don't know, it just seemed like a logical way to address the problem. I guess it could be addressed at another layer by...
This is let us help you avoid security pitfalls that we know about.
Yeah, I'm not sure what the security pitfalls of DAE would be. It has a security proof behind it. It's in the Rogueway and Shrimpton paper. So,
Chris Wood, I know this is like an adopted document, but I'd like to suggest that perhaps we split it into two. There are like two very different use cases that are being addressed by one specific document, one of which is like very simple and small, that is like the compact representation. Put that in a separate document. We do not need an RFC for it. You could just keep it in the group because it's already been adopted on the basis of the being in the ID. But like we just went through the registration process for getting a new chem in the registry. It was super easy. It's already deployed. We don't need to really be spending so much time on it. And then that would allow us to focus this draft on like the.
How do I get a new chem assigned, and how do I describe the serialization and deserialization?
You just need a draft that has a stable reference, like so. Just write an ID, and you follow the process for registering it that's described in the IANA registry. That's all you need to do.
Okay.
Actually, I mean, same for the AAD actually as well. Like we don't need RFCs for any of this stuff. The whole way we designed HPKE was specifically to make it super easy to add things like new chems, new AADs, new KDFs, provided they satisfy the security contract that HPKE requires. I'm not suggesting like don't do this, but I'm saying like let's like spend less of the group's time on things that could be dealt with in an email.
I hope you don't mind if I ask you to hold my hand in the process, but
of course not.
Okay, all right, good. Okay. So very good. Thank you.
All right. Thank you. Okay, Bjorn next.
Okay, so thank you. I'd like to give you an update on the CPACE draft, which deals with symmetric password authenticated key exchange. Next slide, please. We've just uploaded version 8, which is essentially unchanged since version 6, so quite stable in our opinion. So I'd like to recall the objectives of the last major rewrite, which was for version 06. So where we try to focus on the implementer and protocol designer perspective and a lot less on the security researcher perspective, as we now have very detailed papers. So the draft tries to facilitate the integration in existing frameworks such as TLS which come with a clear initiator and responder role, and which come with specified message encoding formats on one side. But we also wanted to provide an explicit encoding format or explicit prescription on how to use CPACE in a standalone construction where which might have been built up from scratch. So, and coming back to the as a consequence of the discussions that we had in the PAIC selection process, we have seen that there are two use cases. One use case where we are having a message sequence ordering, which is enforced by the protocol, for instance, such as for TLS. But we also have applications, we have had discussion on applications where we have no ordering of the messages from both parties, and we try to cover this this aspect also in the draft in order to make it clear on how to use CPACE if you don't have an ordering, as in TLS, for instance. And finally, we had added comprehensive test vectors. So next slide. Since version 6 of the draft, we had received quite some feedback from people that have implemented and worked with the draft and have contacted us. Unfortunately, mostly the discussion has not been carried out on the list, but privately. Interestingly, the most feedback that we got from implementers actually did use work on implementations of the Ristretcher and decaf cipher suites, which are shown in the draft. And on the other side, we have received some feedback which advocated for rather not pushing the Ristretcher and decaf cipher suites in order to reduce the complexity and focus on less of platforms, so that, for instance, to give more focus on the NIST curves and standards short wire stress representations. So we as in the editor team, we understand both perspectives. And we'd appreciate some feedback on how to deal with recommending cipher suites and what to include in the draft and not include in the draft. We don't see any security issue or security difference from for the different variants. It's rather a policy topic, or it's not a security issue anyway. And so what we are currently doing in the draft is that we include the test vectors and a detailed description also for Ristretcher and decaf. And I think my personal opinion is that it's a good idea to have them included. But presently, we're not adding these cipher suites to the explicitly recommended list of cipher suites. So, but we appreciate some feedback there, and probably it's a policy issue. There will be both opinions or different opinions around. So, next slide. So, as we didn't see a lot of objection or difficulty regarding readability from the feedback, we think that we might go further and proceed with maybe an editorial review by some native speaker would be helpful to get the write-up improved. And I think it might be the time to start an official review by the crypto review panel, maybe in 1 or 2 weeks, so that we get further with this with the draft. So coming back to one topic of self-contained write-ups, I can confirm that it's really helpful to try to have all information that a reader needs in the draft. For instance, my plan is also to add test vectors for all the building blocks for the recommended cipher suites also in the CPACE draft. For instance, to add also test vectors for the hash-to-curve suites, which we use in recommended cipher suites, also in the CPACE draft and not only refer to the hash-to-curve draft, because it seems that at these interfaces where between the different components, that seems to be an issue for or difficulty for the implementer. So probably it's a good idea to have the information somewhat redundant and have it of the same turf content so that the implementer finds any test vector for all the building blocks and the entire final protocol in one draft. So that might help help implementers. And we had some feedback or questions which dealt with this interface. So, and similarly, we are planning also to add JSON encoded test vectors because this might really help some implementers. Probably we will be adding it not to the draft, but rather to the reference implementation, which we use for deriding the test vectors. So thank you.
Chris Wood, on the Ristretto decaf question, you said it like some of the feedback was that it introduces additional complexity. Did you mean to say that the complexity is that the text is longer or the document is longer, or that using Ristretto and decaf somehow made the protocol more complex? I assume it's the former, but I'd like to just clarify.
I think it might be both. It might be both. Obviously, if you have people which don't like Ristretto or the idea of the concept of Ristretto so much, they also will complain about the longer document. I think it's somewhat it's difficult. We just received the feedback. Oh, maybe rather make the document shorter and easier to read and leave out Ristretto. But I think now that you are using Ristretto also for opaque, I think it's a good idea, and that's now that Ristretto and decaf is more far in towards a real RFC. I think it's something which probably should be kept. That's my personal opinion.
Yeah, that would be my suggestion as well. And that's a good segue into my next comment, which was, we have these two different drafts that are both specifying some form of like opaque. It would be fantastic if we use like very consistent terminology notation across both. Hopefully we have this other group draft in the document or draft in the group that talks about how to present things in a consistent way. Let's like follow the advice of this document that we just adopted that we think is good, and make sure these two things are unified with respect to like terminology, notation, and stuff like that. So like as a concrete example, how you express like scalar multiplication and in the opaque document should be exactly the same as how it's expressed in CPACE. I do not care which one it is. I don't have a strong opinion, but like let's just please make sure that they're consistent.
So there's one feedback that I'm having also to this original draft regarding the write-up, because I'm having sometimes the impression that we have different perspectives on the intended audience. Yeah? So some drafts might be really targeting the research community, and others might be rather focusing on the implementer. And I think we might not always have the same understanding of the reader audience, and so we might having different focus on different aspects. And this might also be something for this overall RFC or draft, which describes on how to write up the specifications, so to get a more clear picture on the audience that we are targeting.
I think one of the things that's in the document is that there are multiple audiences for a document. There's first and foremost, there are implementers, because that's why we're here, to like implement things. And then there's also people who would like security researchers who would look at it to make sure that it's correct and consistent with what's actually been proven. So I think that's already in the document. Like in my perspective, that like targeting that audience should be our like the first priority, because if we can't specify something in a way that's like implemented correctly, then we've already lost the game. Anyways, that's it. Thank you.
Chris Patton, I just wanted to quickly double check something. You in CPACE, we don't actually use the group operation. Is that right?
In CPACE, we don't use a group operation. Yes, we are using just the scalar multiplication, and you don't need the full group operation. Yes.
Okay, that might be. I mean, I don't disagree with Chris Wood. Consistency is the main thing, but if folks wanted to cut ristretto and decaf, X25.19 and X448 would probably be good enough if we don't need the group operation.
Yeah, and that's what we're currently having as recommended cipher, because it's also one of the points is that it's less overhead and it's easier to implement basically for very small targets, and that's where CPACE is coming from, because we had a Cortex M0 with only 1 kilobyte of RAM for the crypto operations and wanted to get good security, and if you're having so small targets, then also the overhead for ristretto and decaf adds on some complexity and implement and code size, and that's. But on the other hand, it's much easier for the implementer because you get the mapping delivered with the abstraction layer, and so it's easier to implement, and for a PC-based or larger system, there's virtually no difference.
Cool. I think that's a great place to land. Thanks.
Armando Faz from Cloudflare. I think I can volunteer to do like a quick revision between getting consistency between opaque and CPAC. And yeah, about the group operation, I think it's the slight difference is because you're using operation on the X line versus in opaque doesn't use that. So I can provide feedback to that.
Mm-hmm. Actually, I'm quite convinced. I'm convinced that also opaque could be implemented without group operations. I'm sure. Essentially, you need the same properties for the mapping operation, which is the invertibility of the map, the probabilistic invertibility of the map. So you could also implement opaque using X25519 in my I'm convinced, but it's not yet wrote up, and we discussed whether to write a paper on that, but we didn't find the time or didn't focus on that.
Yeah, okay, yeah, I think that that suggestion reduces to make OPRFs on the X line. Okay, thanks.
All right, thank you very much. Kevin next. Quick update on OPAC.
All right. Yeah, so I guess there's already a bit of discussion about opaque, but I'll kind of go over where we are with the current status of the draft. So I'm Kevin Louie. I'm representing the authors of the opaque draft. Next slide. Okay, so I guess for those who are unfamiliar, opaque is basically a protocol which takes an OPRF, a hash function, a memory hard function, and something called an authenticated key exchange protocol, or AKE, and turns that into something called a strong augmented PAKE. And this is in contrast to CPACE, which does symmetric PAKEs as opposed to asymmetric or augmented, is what they're also called, PAKEs. And as an example, we have a set of recommendations of configurations which are recommended, which are below, and we include ristretto as one of them. This is essentially inherited from the VRPRF draft, in addition to P56. Next slide. So in opaque, there are essentially two phases. There's an offline registration phase, where a client, you can think of, similar to when you're registering an account for to a web server. You enter a password and you register some credentials with the server. And then there's the online login phase where you then are expected to enter the same password. And this is where the authenticated key exchange portion comes in. And for opaque, or for this draft, we're specifically focusing on a specific authenticated key exchange called 3DH. And we know, because we got some feedback early on, that in the future we could support different kinds of AKEs. And we kind of have limited the scope to focus specifically on 3DH for this draft. Next slide. Yeah, so the last time we presented about this was about 2 years ago in IETF117. And since then, there have been a couple changes that have been made to the draft. One is that we've made a separation between the group that is used for the OPRF computation versus the group that is used for the authenticated key exchange portion. So previously we assumed that these would always be the same group, because why would you ever make them different? But we got some feedback for use cases which preferred to use a different group for AKE. So we kind of supported the flexibility to have these be different groups. And I believe we don't have, currently in our recommended configurations, it's always to use the same group, but in theory, someone could extend it to have the AK group be different. And in fact, I think we support, yeah, so the next bullet point is that we had test vector support for the AK group specifically being different from the OPRF group. And in those test vectors, I believe we have the OPRF group being like ristretto, but the AK group being curve 25519, where the key exchange function is x25519. And then another kind of major change is that in the last IETF presentation we talked about the introduction of this envelope mode concept, where we had this concept of internal versus external. So internal was like normally, and in the OPRF, like you can use the output of the OPRF to derive a secret key that you then use for the AKE portion, and that's considered internal mode. And external mode is like you can bring in your AKE private key from somewhere else and just use the OPRF derivation to like wrap or like add a layer of encryption around it. And we've decided to actually get rid of this layer of complexity and just focus on supporting internal mode for this draft. And again, with the idea that if there are other implementers who would like to have the external version where you bring in your own AK private key, that this would be an extension to the draft, and that we've specifically written the draft in a way that allows for this extension. And then some minor changes are, I guess, just keeping in line with the VRPRF draft, the latest version, since it's a dependency, and a bunch of editorial improvements, which include clarifying some of the language around the security properties that you can get out of opaque, how it's used in practice, things you have to watch out for, and so on and so forth. Next slide. Yeah, so I think at this point we've addressed most of the feedback on the GitHub page, but of course, if there's if anyone reads the draft and wants to leave more feedback, we are usually using either the list or the issues on the GitHub page to kind of talk about that. But at this point, I think we're ready to start a crypto review panel. And hopefully we also would like to move towards an RGLC for the document. And that's it. Thank you.
Any questions for Kevin? Any comments on unifying CPACE and opaque from your perspective, Kevin? Have you had a chance to?
Oh, yeah, in terms of the, Yeah, it's been a while since I've last read through it, but I mean, I think I agree with Chris in terms of like trying to at least have the drafts read similarly, like instead of using like, you know, different notation for things. I think that would certainly help. Um, yeah, so the discussion that was following the previous one about like support for Restrata, for instance, I mean, it's a little different because we support Restrata and opaque because that's just what's done in VOPRF. So like it would be a little, it seems like it would be weird to not support it. I don't know if, or I guess I can't really comment too much on the complexity of supporting that for CPACE, but it seems like it would be nice, at least from from the implementation perspective, to also support Restrata. That's just my personal opinion, I guess.
Okay, thanks. So we still haven't been able to get a hold of Frank Dennis, but if you, or Denis, if you have heard from him, I've sent him an email. We're going to continue to Joe Harvey.
All right. Good afternoon. I'm Joe Harvey, and I'm here to talk to you about Merkle tree ladder mode, or MTL mode signatures. We were looking at this from the perspective of, with post-quantum impacting many different things, we need to think about, can we do things slightly differently? Key agreement, post-quantum key agreement, can we do CAMs? Signatures, what can we do there to make this, you know, use the things we have and make it more efficient? So next slide, please. All right, so MTL mode is a method for reducing a signature's operational impact on an expanding message series. What does that mean? Well, there's a bunch of data series like certificates or DNSSEC where you sign a bunch of things and over time you add more things to that set. But at the same time, you want to send the signatures out so that multiple verifiers can later check those. It's not necessarily right at the time of signature, but it's sometime in the future. So we need a way to do that and do that efficiently for the signer, for the verifier, and for the protocols. So how does this work? We create a node set. A node set is essentially a Merkle tree, but it's the complete binary subtrees within that Merkle tree. The root of the Merkle tree will keep evolving, but those binary subtrees are going to stay the same or slowly evolve as the message series grows, you know, log n growth of the tree versus constantly changing. If we take the leaf node in that tree and trace it up to one of those roots, we have an authentication path. So we can verify that the message is within a tree, and we have a root that we can verify against. If we collect all those roots of those subtrees, which we call rungs, and put them together in a set called a ladder, we now can verify all the messages across all the binary subtrees using one of the rungs in the ladder and the authentication path. So the ladder then lets us sign the tree to sign all the roots and use them for verifying our messages. The nice thing is, because the trees are evolving slowly, if you have a ladder, you can verify all the stuff that you have now, and you only need to go get a new ladder if there's a new message that you didn't already have covered in one of your sets. So it gives you a nice kind of backward compatibility, and you only have to go fetch the ladder if you need it for something new. Now, that might sound a little scary. You have to go get the new ladder, but we've done some studies about how much you have to do to go get that. If you look at Bert Kaliski's presentations from NIST and from the CTRSA, he talks about endurance, which is how often you actually need to go get the ladder. And for things like DNSSEC, it's actually not as often as you might think. All right, and just to explain where the mode comes from in here, we are thinking about how do you couple these things together differently, kind of like how block ciphers had different modes of operation. You had different encryption, you kind of plugged them together in different ways. We're taking different signature schemes, we're aligning them with hashing functions to MTL's hashes for cryptographic separation. And so that's kind of where the thought for mode came from out of this. Next slide, please. Thank you. All right, so the benefits of MTL mode, it's a hash-based scheme, so it gives us some post-quantum safe design. Because we're evolving a tree, there is a state, but the nice thing about this is it's not like stateful hash-based signatures where if you lose your state, you could compromise your private keys. In this case, if you have an issue with the state, you might get an additional pre-image attack because you might reuse one of your hashes. So it degrades very gracefully instead of being a security issue, losing your private key potentially. The hash functions are available on many different hardware platforms. So from a performance standpoint, there's a lot of optimized hardware and libraries that can do the hashing. So if you had a concern about, for example, the floating point math in Falcon, you're only doing that once in a while when you sign the ladder instead of having to do that for every single message that you want to sign in the series. The proofs are typically much shorter than the PQ signatures. So in our studies, the things we looked at, the signature sizes for the authentication pass were 200 to 400 bytes. That's in the ballpark of what we can handle today with a lot of different protocols. RSA and others are a couple hundred bytes. So the signatures are short. They're easy to store in memory. They're easy to transfer across the wire, and it's easy for a validator to check those. And only occasionally do you need to go get the ladder and the PQ signature, which is the thousands of bytes. We can also make it more efficient for signers because we can batch them together. If you're signing a couple hundred messages, you can build the node set all at once and then sign in the end. So instead of having to sign 100 messages with a post-quantum algorithm, you can do the hashes that are fast and do one signature. And that also has a benefit for hybrid signatures where you could sign the ladder with multiple things. So you're signing once with multiple algorithms instead of having to do four algorithms, 100 messages, 400 times. Okay, so so it makes it easier for the signer to sign and store. It'll potentially fit in UDP packets like for DNS, and then also the validators can store these in memory and cache them, and it uses a lot less memory to do that. So some of the benefits of it. All right, next slide, please. All right, looking forward to the guidelines draft. I read through a whole bunch of CFRG drafts. I looked over that and put this together, but those guidelines are helpful, especially for things like the annotations and the symbols that you use and all. So you'll see in this draft, we talk about kind of the general constructs, how to put it together, how to use the different elements. In sections 7, 8, and 9, we get into the specifics of the bytes, how to arrange it, how the algorithms work to do the different operations. Section 10, we talk about how to align it with Sphinx Plus. So we need to ensure that a lot of the signature algorithms hash when they first get the message. We need to make sure that the hash is going to be cryptographically separated from the hashes that are happening in MTL mode. So we went through and did that for Sphinx Plus because they line up nicely together being two hash-based systems. So that's explained in Section 10, how to use the PRF, how to use the different hash functions. Section 11 talks about some related work that's in the area, and also the references section at the end there has a bunch of the things in the document, but also links to those research papers that I talked about from Bert and others that talk about this. It has the security proofs in there, and it talks about the different things like endurance and how some of it all plugs together. Next slide, please. All right, intellectual property. So we do have a declaration for our no obligation about intellectual property. We would like to see this become a standard, and we recognize that we need to explain the intentions and how we see that. So there's also a blog post as well about this. You can see those documents for specifics or contact information if you have questions about those specific elements. And next slide, please. All right, and next steps. So thank you for giving me time to talk today. Thank you for in advance for any feedback you have on the draft. CFRG mailing list is a great place for feedback, but if there's other ways that are good to get feedback on this, I would appreciate that input as well. We're working on an open source library that will combine MTL mode with Sphinx Plus. So there'll be a implementation of it. That will include tests. I know that tests have been a big topic here the last couple of IETF meetings that I've participated in. So there will be tests in there. They'll give the examples. They'll help verify things are correct and help to validate it. We're going to do an internet draft on using MTL mode with DNSSEC. So that'll give kind of a use case example of plugging it in. The plan is to take that to DNS op. But again, if you know of other groups that might be interested, that input would be interesting as well. And finally, I tried to match the style of the pseudocode as much as I could to other documents, but we actually made the pseudocode in Python so we could validate that it's doing exactly what we said it's doing. If you look at Appendix A, we've collected all that together. So basically you have a Python version of the high level concept here. Appendix B includes stubs for underlying signatures and Python tests. So you can actually see the operations, play with it, experiment with it, and see exactly what we're talking about. So if you're a hands-on person, you can do that as well to see what's in the draft. So with that, I'm here all week. I'd love to talk to you if you have questions or would like to learn more about it. And I'm happy to take questions.
Mike, go for it.
Mike Ainsworth. So I've a comment and then a question. My comment is sort of equally addressed to you and to the authors of the Merkle Tree certificates stuff. One of them is right there. And the other one's over there. These two drafts sort of superficially look fairly similar. You're batching hash. I know that they are different. I would love to understand how they are different. I don't know if we can sort of facilitate a discussion on what the similarities and differences and benefits and between these two, MTL and MTC. My question is, I've already put it on list, so I'll just read what I posted on list earlier. Has to do with your benefits slide. So it's not sort of immediately clear to me who gets the benefits, whether it's the signer or whether it's the verifier, and under what circumstances they get the benefits. Is it only if you're doing large amounts of signatures, or only if you're verifying large amounts of signatures? And which IETF protocols in particular sort of work in those modes where they get the benefits?
Okay, so both the signer and the verifier can get benefits because you're only storing, you only have to store the authentication paths and one ladder. So for computing and for storing that in memory, it uses a lot less resources to do that. So from a signer side, it's easier to sign once and hash a bunch. From the verifier side, again, being from VeriSign, our perspective, a lot of things is DNS. So, there's already things being cached. If you cache the ladder in your resolver and you're verifying, if you've already checked that signature once, then you only have to take those smaller auth paths and verify them back. You don't have to check the additional signature you've already cached. So again, you only have to store the ladder once. You only have to store the auth paths once. So it saves resources and computation, both for the signer and for the verifier.
So is there a tipping point then? If you verify a single signature, you're taking overhead, but after X, you're benefiting?
Yeah, so if you look in the research paper, and I think Bert actually sent something about that on the list. We talk about how many times you can verify versus how often you need to fetch the ladder. It's the discussion on endurance. So if you look, you can see kind of that benefit of, there's rates involved, right? Like how many times you're going to query versus how many things are published in the meantime. So if you look at those trade-offs, you can see some of the math in the draft.
Okay, and then protocols. So you mentioned DNSSEC. Is there other places in IETF that you think this would fit well?
Probably. I mean, that's part of the feedback we're looking to get, is where do people see it, fitting well.
Hi, Philhan Baker. Yeah, I like this stuff. I've done similar with the data at rest envelope and sequences. It's the way that we should be doing things like distributing software. So you can have a distribution and sign every little file in that distribution, including the ones that, be executable for the Mac that you've not got because you're on a Windows box. And so there's a whole host of stuff like that that's really useful. In the other area it pulls into, and Keytrans didn't meet this time, but it's adjacent in that they're doing something slightly different. They've got a log file that is, so then they're re-signing it. But one of the things that has always struck me about, when we get into the post-quantum signatures, there's two types of signature I'm interested in. One of them is for, I want to be able to update the code running on this machine. So that if, I've got to move to the post-quantum crypto that comes out in 10 years' time. So that's one area. The other area is non-repudiation and signing stuff that somebody's going to trust a signature in 10 years' time. And when we looked at that, 20 years ago, the reason we didn't use blockchain technology wasn't that it hadn't been invented. Haber and Stinetta invented it in 1990, thank you very much. But there was a patent on it. And it strikes me that if you're going to care about a signature in 20 years' time, want to verify it in 20 years' time, you probably want to have it a notarized signature. So when you're thinking about this sort of technology, working a way into turning it into a notary scheme or interfacing to a notary scheme is probably also worth doing. Thank you.
Watson Ladd from Akamai Technologies, Merkle tree enthusiast. So I am not sure I got a great understanding of what you're doing. It's sort of the idea we're signing this root, and then so long as you know, as you have a chain somewhere up to somewhere in the root you've seen as a client verifying this, you're fine. And maybe down the line you'll see another signature that's claiming a chain up to something you haven't seen, and then you go grab the big signature that's sitting off somewhere. Is that more or less it?
Yeah. So you can verify a set of messages, and if it's outside the message, newer than the message, then you need a newer overarching set of the new signature to be able to verify the new stuff.
Yeah. So one of the things that I think, and this is sort of thing you'll work out as you develop a draft more, sort of that ultimate signature, you also need to worry about size. If you have a size constraint. The other thing is I'm thinking in terms of like the web environment, where you have a privacy concern when the browser is going out and fetching something from a third party dependent on the certificates. That is a problem that would also need to be addressed to apply it there.
Okay, thank you.
Yeah, Joe I'm one of the co-authors on the draft, and I would just encourage people who have questions to read some of the reference material at the end of the draft. And there's some good stuff that covers the DNSSEC use case and explains, which is a very good use case for we think for MTL mode. And you'll see other similar use cases, that there are out there. And you'll probably recognize them. And also Joe and I will be around this week, and because we know it's kind of a different model, and we're here to explain it to people who want to learn more.
Thank you. All right, thank you very much. Aaron is CAM combiners.
Yeah. Hi. This is a very brief update onto the CAN combiners draft. It is draft to combine CANs for hybrid cryptography in the post-quantum setting. Next slide, please. So we have done a few changes from version 03 that was presented at the last IETF, and we removed the hashing step because this makes it lighter, significantly lighter. We turned around the parameters so that the construction can be used easy for streaming data. We prefer the KMAC-based constructions because they seem to be lighter than the SHA-3-based constructions. And we ditched the term that I made up multi-PRF for a more formal split key PRF. Next slide, please. So we still have these three issues that are open from the feedback we got privately or on the list. And first of all, we rely heavily onto the random oracle assumption for Ketchuk, and we should probably clarify that better in the draft. Then also we should give some guidance on how to choose the KMAC key, and especially give some default values that do not overflow the block size as we have been recommended. But we need to understand whether it makes sense to give a default value at all, or whether we should just guide implementations how to pick one. And the last one, it's a bit the most complex one, is whether we can consider HMAC SHA-2 based constructions given a certain amount of constraints and assumptions that I invite everyone to check out the issues in the repository and make comments there, because we found a nice paper, but I'm not sure whether it can be actually used. Next slide, please. So this is the current construction we came up with. We have, it is compliant with SP 856C, and that's why it has this shape. But then the way we changed it is basically by adding the ciphertext followed by the length of the ciphertext right encoded, so that we do not know the length a priori, and then followed by the shared secret, so we can just read the ciphertext as we're passing it to the algorithm that will generate this shared secret, and this will also, we just need to keep the hash state without having to keep the whole ciphertext around to hash it later. And this can be done for multiple cans, and as we decrypt them one at a time, and followed by some fixed info that is protocol specific. Well, I hope we can try to get adopted after all these other RFCs may have come out or gone into RCLG. Thank you. Any questions?
Doesn't look like there are any questions on the list or questions in the queue. So with that, any other business? We have 2 minutes left. We don't have an update from the presenter for Aegis at this point. The slides are online, and they have a lot of information in them. Hopefully we can get a hold of the presenter. Okay, thanks everyone, and thanks everyone for coming. Actually, last minute, we do have an opportunity. The presenter just has shown up last minute. So if folks want to stay, we can do a quick presentation from Frank.
Here we go. So hi, I'm Frank Denis, and I'm going to give you an update on Aegis.
Frank, just to let you know, we're right at the end of the session, and if you want to delay this to next time, that would be that's something we can do. Otherwise, like a 1-minute summary is sort of what we can squeeze in.
Okay, let's try to do a 1-minute summary. So Aegis is a cipher for high-performance applications. It has some interesting properties missing from the currently standardized ciphers. Next slide. So next slide, yeah. So we addressed all the feedback we received, which was mostly from people writing implementations. We didn't make any breaking changes, so the current version of the document remains compatible with all existing implementations and deployments. There's been additional analysis that gives us confidence in the construction and the parameters as currently specified. We just made an incremental addition to add the ability to use larger authentication tags that has practical advantages for some protocols. We added guidance on how to use Aegis in TLS, DTLS, and Quick, and IANA assigned identifiers. So it's possible to add Aegis to this protocol today and verify that implementations can interoperate. Next slide. So there are a bunch of implementations today for all major languages written independently. So we are quite confident that the draft, as it is today, contains everything needed to write an implementation from scratch. Next. So Aegis has also some real-world deployments, and it's even supported out of the box by a TLS stack. Next. So Aegis heavily relies on the AES forward one function that a lot of CPUs implement natively, but some more recent CPUs have the ability to do that operation on vectors. So the next revision of the draft is going to specify 2 additional optional variants of Aegis, specialized for these high-end CPUs. This is not going to require a lot of changes to a draft. These variants are built on top of what we already have and share exactly the same properties. Next. So these new variants are super fast on these specific CPUs. They can take advantage of vectorized AES, and Aegis is twice as fast when using these vector instructions. Next. So even on recent high-end CPUs with 512 bits vector registers, pretty much all VES-based constructions can take advantage of the new vectors. However, a generic implementation remains faster than the fastest AES GCM implementation today. And if we take advantage of the large vectors in Aegis as well, then the performance doubles again. Next, and even the 256-bit variants of Aegis and AES GCM can take advantage of that. But with Aegis, the performance triples. So next, the main change that we are expecting in the next revision of the document is the addition of these specialized variants. Otherwise, no major changes are planned. The constructions are unlikely to change, and the document should soon be ready for review by the crypto panel and then the RGLC. That's it.
Okay, thank you. That was a speed run and very impressive work. We can do one more question, and if not, I think we're over time. So thanks everyone for coming.
Thank you.